Hello, I'm Cortland Sterrett, Engineering Manager at Mentor Graphics, and I'm going to show you today a tool set called BridgePoint. BridgePoint is used to model and do engineering development for embedded systems combining embedded software and hardware. I have here an embedded controller board used for prototyping. This one happens to have an ARM 7 microcontroller on it, and I'm going to show you how BridgePoint would be used to develop embedded software for GPS, Global Positioning System applications. I happen to be a runner, and I use GPS in a running watch that captures the information from my runs and allows me to analyze them afterwards. And this running watch uses an embedded controller very similar to the one on this board, and we will go through the steps of developing the embedded application for GPS using BridgePoint. With BridgePoint, we will model the GPS application, ultimately allowing us to generate code and build a complete system. BridgePoint UML is distinct from other modeling tools in many ways. UML modeling allows us to approach engineering development at a higher level of abstraction with a reduced level of details and allowing us to focus on the problem at hand, and in our case, GPS. We can do system level modeling that allows us to build individual components that can be reused, thus capturing and being able to maintain our intellectual property in a reusable way. BridgePoint performs executable UML, so we can begin executing and therefore testing and verifying our application right from the first day that we begin modeling. The models that we will build are platform independent. What that means is that I can change the target and maintain the integrity of my model because I have built a model that is not dependent on details of the target. And translation allows us to take that platform independent model and generate code for platform specific targets. The framework that we'll use in the demonstration here is that we'll basically go through all of the steps of modeling and development to ultimately get us to a running target. And the modeling aspects include system level modeling, where we will break the system down into its various components. We use component diagrams and interface diagrams for this work. We can also augment those with use cases, sequence charts, and other documentation-oriented diagrams inside BridgePoint. Once the system has been broken into its components, we can model each of those components then, beginning with class diagramming. The class diagram will capture the data aspects of the system. Control and sequencing is done on state charts, and we'll see each of these inside the tool as we move forward. At the lowest level, the model has to actually execute and do things and perform processing. BridgePoint uses an action language for this, which you will see inside the tool momentarily. Let's talk about system level modeling inside BridgePoint. BridgePoint is an Eclipse application that will then integrate with your other Eclipse plugin applications. And our first view of the GPS system is the component diagram, which allows us to do system level modeling. We've broken our system into three components: a cycle counter used when I'm riding my bicycle actually, a heart rate monitor, and the actual GPS system itself. The component modeling allows us to break the system into reusable partitions, in this case components, with formalized interfaces between them. This is useful to give us a view of the system from the individual black box components, and it lets us reuse them. Inside each component is an application model, which we'll look at next. The first step in component modeling is to capture the data perspective of your application. And we use UML class diagrams for this. This is one of the more familiar UML diagrams that allows us to focus on the entities of the system. And in a global positioning system, you would expect to find satellites. And so we have a satellite class. The satellite is used to triangulate individual points that the GPS acquisition is collecting. Points have attributes, and in this case including the latitude, longitude, and elevation of each data point that's collected during my run across town. Points then are associated with a particular route. A set of points ordered in a sequence establishes a route, and we've captured that information here in our class diagram. Individual classes then have dynamic behavior, and in this case the route class has a state machine used to define its behavior over time. Every instance of the route class obeys the rules of a finite state machine that we build to govern its various states. In this case, routes begin from starting, and then they're collecting data points, adding those data points to the route in a particular sequence, and then eventually when I push the button again on my GPS, I go to the finishing state. Control and sequencing in our application will be captured, documented, and tested in BridgePoint using finite state machines. We can also support and augment those with use cases and sequence diagrams at the class level. Inside each state, we have captured the behavior of the processing that occurs in that state. In BridgePoint, we use an action language. And if I look at the collecting state, I can see that while the route is in the collecting state, I'm going to create an instance of a timestamp and create the point and relate it to the route, and then generate an event causing me to move to the next state. The action language is the key to platform independence. Instead of typing code, platform-specific code, into my models at this point, I'll use an action language that is platform independent. Later on, we'll see how this allows us to execute these models before I have a target, and also to generate code that is specific to the target from this platform independent action language. Let's continue the process. We have now built a platform independent model of GPS data acquisition. We've gone through and broken the application into individual components. We've modeled those components using the class diagrams, state models, and action language. Now I would like to verify that my application is correct and actually build it. So we'll continue the process by executing these models in an interpretive fashion using the model verifier portion of BridgePoint, after which we'll generate code and run it on the target. Let me show you the model verifier executing the model. I've launched the verifier on the GPS, and I'm showing the route state machine in the middle window. So I will execute a setup function which will run some action language that will create initial instances of some of the classes in our class diagram. And I have a route which I will place in the spotlight to allow us to dynamically watch it step through its various states in the finite state machine. And let's virtually press the button on our GPS application by executing the function button pressed. What we see is the state machine going through the various states, and we see it animated in the middle pane, and we can see instances of GPS points being collected, each one of those points having the latitude, longitude, elevation, and being collected into the route. And the route will collect points 1 per second, add them to the route until it transitions to the finishing state at the end. So we now have a 30-second route that, had I been running around the town or the countryside, would have been collected into a route that we could display. So I've now executed and verified that my model behaves as it should, haven't generated code yet, and I'm simply running inside the tool, allowing me to do testing very early. While running the model verifier, we've demonstrated that BridgePoint Executable UML is executing models. These UML models are actual semantically complete executable units. They're not just pictures, or they're not just diagrams. We can begin testing our application from the very first day that we begin modeling. This allows us to remove defects earlier and cheaper. We can characterize the behavior of the entire component and perhaps the entire system before we've begun coding it or placing it onto the hardware, where defects are more difficult to find and more expensive to find. Once we're happy with the behavior that we have modeled, we can then continue the process and generate code for our application. Since we've done a large amount of early testing, we can be confident that we'll get the behavior that we expect. So let's look at model compilers inside BridgePoint. BridgePoint allows for open, flexible code generation, and once I've built my model, I can simply build it. So I will build the project, which will invoke the model compiler and begin the translation process, generating the code, and in this case, generating optimized C code that's meant to run on an embedded target. The process of model compilation will use a set of templates that govern the shape of the output code. And note that once the model compilation has completed, we can see some of the generated C code, which we can then compile and use just like we would handwritten C code. Compiling models is not magic. The process works this way. The application models that we've built in BridgePoint are one input. We have a model compiler, which is a set of rules and templates that are used to govern the shape of the output text. C code is simply a specific shape of text, and we have templates that are used to govern the choices in how models are turned into code. One additional input that is supplied during this process is marking. Marking represents the options that are used to determine the types of optimizations, the types of choices that we want to be able to change easily when we're generating code. Example markings include choices of space versus speed, or specific rules in the patterns of the way that data will be stored and managed in our generated application. These three inputs are supplied to a translation engine which combines the three and outputs the generated code. Once we've generated the code, we'll compile it and link it with legacy code. Virtually every project that engineers work on has some amount of code that has existed ahead of time. Modeled models and the code generated from models can be integrated with that legacy code very easily, and we compile it with the choice of C compiler with target options that we want. After building the models, executing them, and generating the code, we've now compiled it for the target and downloaded it onto this ARM7 microcontroller prototyping board. And in this particular board, as the application's running, each time a GPS point is being collected, one of the LEDs will blink so that we can see the outside behavior on the board. So now we've seen all the various steps of developing an application using Executable UML on BridgePoint. We built component diagrams, class diagrams, state models, and action language to capture an executable specification of the behavior of our application. We then ran that with the model verifier to ensure that it had correct behavior. And then separately, we generated code, compiled it, built it on the target, and ran it. This separation of the specification of the application from the implementation of the target is one of the distinctives of BridgePoint. This allows you to capture two sets of intellectual property. One is that the subject matter experts, the people who understand global positioning in this particular application, or any application that you may be building, can capture the definition of that application in platform-independent models. Separately, the implementation experts can focus on the model compiler, which is, again, reusable IP that can be used to translate any executable UML application for a specific target. This reusable IP allows you to specialize the experts in your departments, as well as capture and carry forward and reuse these distinct bits of information. And if the application and the implementation are mixed together, they're not as reusable. It's more difficult to move an application from one platform to another if platform details have been built into it, and it's more difficult to capture those architectural platform specifics and move those forward if it's completely intermixed with the application. The model compilers represent reusable IP that allows you to take multiple applications and target them to a specific set of microcontroller, programming language, strategy for storing data, embedded operating systems, and the model compiler focuses on those platform details. Note that there are three ways that we can use BridgePoint to develop applications. BridgePoint is, first of all, a UML tool, which allows you to draw diagrams. Drawing diagrams gives you the strength of UML in its diagramming is communication. So at the first level, I use UML to communicate the meaning of my application to others within the team, and then I can take those diagrams and write the code by hand inside those diagrams. However, with BridgePoint, these being executable UML diagrams, I could take that a step further and use those diagrams to execute and verify and test my application to ensure that this specification is correct. Then I could go and write the code by hand. If I want to use BridgePoint to its fullest capacity, what I'll do is I'll build these models like we did in the demonstration here, build these models, execute them to verify their behavior, and then I'll generate code and at least determine if that code is satisfactory for my particular target. And assuming that it is, I can leverage the full capability of executable translatable UML. Performing engineering development using executable UML in BridgePoint gives us several advantages. Our productivity is increased since we're working with models that are at a higher level of abstraction than implementation level code. BridgePoint allows us to model at the system level and model the interactions with the various components of the system, whether those components are legacy code modules that are already available, or whether they are the components being modeled by other development groups on the team, we can model the entire system and its interactions. We can then verify correct behavior because we're using executable models, and we can actually run what we're building and see it perform as expected, or when it fails to perform as expected, we can change the model to capture the application correctly. The models that we're building are platform independent. That allows this executability and translatability of model compilers, and it allows us to capture and reuse intellectual property in a more efficient manner. The model compilers separate out the platform-specific portion of the system into the model compiler, so that the details of the target language, the target microcontroller, operating system, various details are captured in one reusable place that allows us to translate the application onto the target where it can run and we can deliver our products to the market. Those are the distinctives of Executable UML. If you'd like more information, you have available to you white papers and technical documentation, demonstrations, and working with our team directly. Thank you very much.